Hey team, in this video I'm going to take you through the normal distribution. Just like the last one, it's only going to be me going through the applications of the normal distribution, and all the theory and formulas and explanations, make sure you refer to your class notes. Alright, so all this is calculator allowed, so you won't have to do any of this by hand. So let's get into it. Example 10. So given that Z is a normal distribution. Okay, so this, as soon as we see the capital Z, that means this has been standardized, right? So I've copied this diagram from the internet to give you the visual of the bell curve. All right. So when it's standardized, our mean is 0. All right. So and our standard deviation is 1, which just makes it easy for you to understand. So let's do all of these. So A, we want the probability that the area, well, what is the, basically this is asking you what is the area between, so Z just means in the standardized curve, all right, we want the area from -2 to 1. Now if it is a standardized curve, then -2 is going to be here and 1 is going to be here, because -2 and 1 just means how many standard deviations they are from the mean. All right, and knowing what the proportion of the graph, or how the proportion of the graph is generally distributed, all right, just makes it easier to show on a diagram. So we want this area for A. Now we go to our calculator and we go probability, distributions. Now we want normal CDF. Our lower bound is -2, our upper bound is 1. Our mean is 0, our standard deviation is 1, because that's given. Press OK. Yep, there we go. 0.8186. Okay. Now for the rest of them, let's just use, I might as well just explain them with the diagram as well. Alright, so for B, we want the probability that, well, we want the area that's less than 1. So 1 standard deviation from the mean is here. We want this entire area. Alright, we always go to 4 decimal places, so go back to the calculator. Probability distributions, normal CDF. Okay, now our lower bound, we just want it to be basically as far as we can go, right? So a very, very, very small negative number. And our upper bound is just going to be 1. And mean and standard deviation don't change, so there it is, 0.8413. Alright, let's do C. So we want probability of Z greater than -1.5. Alright, so -1.5 would be here. The area we want would be everything to the right of -1.5. So here's -1.5. I don't know, probably right now just put some numbers in here. That's 1. That's 1. -2. Alright, let's go to a calculator. So this time we want our lower bound to be negative 1.5, and we want our upper bound to be a really, really large number. All right, 0.9332. Let's keep going. All right, D. What's D? Oh, well, this is more conceptual. We want probability that Z is less than 0. Well, 0 is here. Graph is symmetrical, so the area has to be 0.5. And then finally, we want E. So probability that mod, or the absolute value of Z, is less than 0.8. Alright, so let's quickly just break down what this means. So if mod Z is less than 0.8, then what that means is positive Z is less than 0.8, and also negative Z is less than 0.8. So if we rearrange this equation to get positive Z, then we have to flip the inequality because we're dividing by negative 1. So that means that Z is greater than negative 0.8. So therefore, means that Z is between negative 0.8 and positive 0.8. Alright, so we can rewrite this. So Z between negative 0.8 and positive 0.8. Alright, mark these on our graph. So that'd be just estimating to be around here, negative 0.8, positive 0.8. We want this area here. So norm CDF, lower bound is negative 0.8, upper bound is 0.8, mean is 0, standard deviation is 1, 0.5763. Alright, so that starts you off with how to apply a standardized normal distribution and to find some simple probabilities. When you do this, always draw a sketch. It really helps visually. Alright, let's keep going. Okay, so now the difference here is that, okay, this distribution, this variable is not standardized. Alright, so what we want to do is, well, again, let's draw a sketch. And the mean in this case is 10. So we can label that. And the standard deviation is 2. Remember, this is, so 2 squared is the variance. So we want to find the probability that x is between 9.1 and 10.3. So basically, if the standard deviation is 2, then this, so mean minus standard deviation would be 8 there, and it would be 12 here. So 9.1, just estimating, would be around here. 10.3 would be around here. So we want this area here. And again, we can just type this into our calculator. So we can standardize this one and use the z-scores instead, but we don't have to. We get the same answer either way. So this time we go probability distributions, normal CDF, lower bound would be 9.1, upper bound would be 10.3. Now the mean is 10 and the standard deviation would be 2 in this case. So 0.2333. 3. Alright. So that's a little bit on different ways you can find the probability in some situations. Let's keep going. Alright, now here's more of a contextual example. Alright, eggs laid by a chicken are known to have the mass normally distributed. Alright, so we have a bell curve with a mean 55 grams and standard deviation 2.5 grams. Okay, so let's label that. So if our mean is 55 and our standard deviation is 52.5, well, that means this one would be 57.5, whoop, sorry, 60, 62 and a half. All right, and let's do the same for the other direction. 50, 47 and a half. All right, so A, what is the probability that an egg weighs more than 59 grams? Well, 59 would be here. Probably not exactly there actually. So 50, that's 2.5. So maybe there's 59. So the probability that X, because this isn't standardized, it's a random variable, X is greater than 59 is, so normal CDF, lower bound 59, upper bound some massive large number, because we want everything to the right of 59 or that area. Mean was 55, standard deviation was 2.5. Okay, 0.0548. Okay, now B, smaller than 53, so 53 is probably here somewhere. Alright, so X less than 53 is approximately, so we can type this in like this. So now this time we want our lower bound to be a large negative number, our upper bound to be 53, mean to be 55, standard deviation is 2.5, 0.2119. And finally, let's do C. An egg is between 52 and 54 grams. Alright, so I won't label this one because I think you'll get the idea. Let's just find this on the calculator. Okay, so we want between 52 and 54. Boundaries go first, followed by the mean, followed by the standard deviation, 0.2295. Alright, there you have it. Let's continue. Let's keep plowing along. Halfway there. Okay. So now we're finding the actual z-score, I call it, or that gives you a particular probability. So basically, we're doing the opposite. We're going backwards. So given that we have a standard normal distribution, we're going to find A, so that basically that's a value on here, some value on here, where anything less than A gives us an area of 0.877. Alright, so really useful when we do these types of questions to graph it. So if the area less than A is 0.877, that's almost 90% of the graph, right? So A would be, just to estimate, about here somewhere. Could be wrong, but let's say that's where A is going to sit, because we want this whole area to be 0.877. So what the calculator does is, when you do this, probability distributions, inverse normal now, Okay, when you put in this area, it's the area from the left side of the graph to whichever boundary you're trying to get it to. So let's say, so this area should be from the most left-hand side of the graph is what I'm trying to say. So 0.877, because that's what we have. Right, mean is 0, standard deviation is 1. Right, that gives us an A value of 1.16. So where I put it was very wrong. So 1.16 would be here somewhere. Alright, there we go, there's A. So it was 1.16. Alright, so for probabilities we usually go 3 or 4 decimal places. For the z-score or the value of the variable, we usually do 2 decimal places. Okay, so B, we want Z, probability that Z greater than A is 0.2. Alright, so if the area greater than A is 0.2, then that means A has to be, well, this time we're looking at, so let's just say A is here. We can fix this after if it's wrong. We actually want this area here now, so to the right is 0.2. So since the area under the whole graph is 1, that means the left side of this, of A, is 0.8. So that's actually the area we need to put in the calculator. So this time we want inverse normal, area is 0.8. Alright, 0.84. Yeah, so where I put it was kind of accurate, so I'll just leave it. So 0.84. Alright, maybe I should put in, since this is a standardized normal curve, then the mean is 0, and all these dotted lines just represent the standard deviations away from the mean. Okay, and then C, where do I put C? Maybe I put it here. Okay, C. Alright, so, this time, the area between negative A and A is 0.42. Okay, so that means we have a uniform area on either side of the mean. So let's say 0.42, right? So let's say like here. So that's negative A. That's A. This area is 0.42. Alright, so what we want to do is find, basically we need this area here. So if we half 0.42, the area on the left side of the mean in this section is 0.21. Alright, which means this area here to the left of this solid line has to be 0.29, because these make up, because this will make up 0.5, which is exactly half the graph. Alright, so what we want to do is put 0.29 as our area into the calculator, and it doesn't matter if we're finding A or negative A, because the absolute value of A is still going to be the same. So inverse normal, we want our area to be 0.29. Mean and standard deviation don't change. Okay, so that means A equals negative 0.55. Well, A will equal 0.55. Alright, and that's how we do that one. Let's keep going. Okay, given that, okay, so now we no longer have a standardized normal distribution. Let's see how we can do this. So given that we have a normal distribution with a mean of 15 and a standard deviation of 3, determine X, where the area or the probability of getting less than x is 0.75. Right, so let's label our graph. So the mean is now 15. Standard deviation is 3, so we can probably just do these quickly. Alright, now we want the area to the left of x to be less than 0.75, so 75% of the graph, or of the area, which is, I'm going to estimate that's about here somewhere. Maybe even, yeah, let's just go with this, and let's call this x. Alright, and now, let's say that's 0.75. Alright, so since that's the area to the left, that's going to be pretty easy. We don't need to do any extra calculations, so inverse normal. Okay, our area is 0.75. Now this time our mean is 15 and our standard deviation is 3. Alright, so it should give us 17.02. So where I put it, yeah, just going to leave it there. That matches somewhat. Okay, and example 15. Cartons of juice are such that their volumes are normally distributed. So let's get our normal curve up. With a mean of 150 mils and a standard deviation of 5. So I can put in some values here. 140, 135. Find the minimum, or 5% of cartons are rejected for containing too little juice. Find the minimum volume to the nearest mil that a carton must contain if it's to be accepted. Okay, so that means the bottom 5%, so if this little area here is 5%, right, we're trying to, so if this value was x, right, that would have to be the minimum volume for this carton to have to be accepted, because anything to the left of that, anything smaller than that, is too small. Alright, so using the diagram, interpret the situation, and then from here it's put it into your calculator. So inverse normal, our area is 0.05, our mean is 150, and standard deviation is 5. So 141 to the nearest mil, right? So that's 142 mils minimum for a carton of juice to be accepted. Alright, doing well so far, let's keep going. Okay, now it's where we do a little bit more problem solving, so let's see how this goes. So example 16. Okay, get my normal curve up. A sack of potatoes, sacks of potatoes with mean weight of 5 kilos are packed by an automatic loader. In a test, it was found that 10% of bags were over 5.2 kilos. Use this information to find the standard deviation of this process. Okay, so since we don't know the standard deviation here, right, we aren't able to fill in any of these values, but we do know that 10% of the graph. Alright, so let's just say, I don't know if that's actually going to be right, but 10% is this area, and let's say that this is 5.2. Alright, so we can ignore these for now. Right, but since we don't have the standard deviation, the way we find it is actually by standardizing this. So basically, so if I label this curve X, let's standardize this into another curve, but let's call it Z. Alright, so if we standardize it, that's going to be 0. Alright, now we can use inverse normal. We know that this area here is 10%. Okay, now let's call this let's give it a lowercase z. Now, since we know that the mean and since we know the mean and standard deviation of a standardized normal distribution, we can find the z-score here using inverse normal. So these two graphs represent the same situation, and one's just not standardized and one's just standardized. All right, so our inverse normal, well, we need this area, it's going to be 0.9. Mean is 0, standard deviation is 1. Okay, 1.28. All right, so that means we need a formula that's got standard deviation in it. So it's this one. So x equals, so z equals x take mu over sigma. Now, sigma is what we're trying to solve for, so let's just rearrange first. Okay, now the x value we have is 5.2. The mean is 5, and our z-score is 1.28. So if we just go ahead and solve this, it's approximately the standard deviation, 0.2 divided by 1.28, 0.156. 156. Right, and that's how you can approach questions where, say, the standard deviation is missing or the mean is missing. All right, use the standard normal distribution to help you. And lucky last, let's do example 17. A manufacturer does not know the mean and standard deviation of the diameters of ball bearings she is producing. However, a sieving system rejects all bearings larger than 2.4 centimeters and those under 1.8 centimeters in diameter. It is found that 8% of all the bearings are too small and 5% are too big. What is the mean and standard deviation? Okay, a lot of information here, but again, diagram. Let's make it a little bit bigger. All right, so if we treat this as our random variable, this is our x graph. We may standardize this, we probably will. All right, so we don't know the mean, but we know that 8% are too small. So let's just label that. So that's 0.08. And then 5.5%, so an even smaller area, are too big. So 0.055. Okay. So what we want to do is, since we don't have any more information here to work with, we want to standardize it. So let me put in a second graph, blow that up, and find the corresponding z-scores here at these values, right? So if that's 0.08, okay, then the z-score here would have to be inverse normal 0.08. Okay, since we've standardized it, negative 1.405, just for accuracy. Negative 1. So let's call this z1, z2. So z1 equals negative 1.405, and z2 equals, well, if this is 0.055, when we try to calculate z2, we want all the area to the left, which is going to be 1 minus 0.055, 0.1, all right, 1.598. All right, now let's use this formula. So since z equals x take mu over theta. Oh, should have probably put the x values in. So this was 1.8 and this is 2.4. Right, we can go 1.405 equals 1.8 because this corresponds to this. Take away the mean over the standard deviation. Alright, and then for Z2, I was just wondering whether or not I should rewrite the formula, but I will. 1.598 equals, x, which is now 2.4, take mean over standard deviation. Alright, so now we have two equations, two unknowns, and it's calculator allowed, so let's use that to solve. So let's go into algebra. Solve system of linear equations. We have two equations. So negative 1.405 equals, let's just use x and y, 1.8 take x, so let x be our mean in this, and then let y be our standard deviation in this, and then 1.598 equals 2.4 take mean over standard deviation. Oh, they're not linear, silly me. Wait. So maybe I just do this. Just multiply the y to the other side. Like this. There we go. So x is 2.08 approximately. So using GDC, x is approximately, mean. So the mean diameter of the ball bearings is 2.08 centimeters, and the standard deviation is approximately, let's go 0.2. 0.2. Alright, so a lot of calculator work. Once you understand the concept of a normal distribution and a standard normal distribution and the characteristics of it, you'll be able to apply a lot of these without too much trouble. Alright, thanks for watching, and I'll see you next time.